Welcome back, everyone. I'm Bhavana Chandrashekhar. I'm a Senior Applied Science Manager at Amazon Robotics. And today I'm going to talk about one of our more recent announcements, Vulcan Stow, and talk through like our journey as a group that put together this robot, where we started, how we introduced modularity and whether we were successful or not, and like how that kind of evolved over the course of the robot scaling. To set some context here, um, what are we doing exactly? So this is a brief clip of a Amazon warehouse. To give you the scale of this, this is about, I want to say, 1 million square foot. There are several of these yellow fabric pods in one warehouse. This is roughly around 60,000 of these fabric pods exist in every warehouse at Amazon, and they hold the inventory that Amazon sells. So imagine you're ordering an iPhone case, that's where it's coming from. You're ordering a sunglass, that's where it's coming from. So humans today get inventory into these fabric shelves, and then they retrieve items from these fabric shelves as well. So this is a storage system. The way that we navigate around this storage system, there are drive units that go store these pods out into the field and then retrieve them when someone orders something and you want to pick from it. But what we are going to be focusing on is the action of stowing into these fabric pods. Here's an example of like what these look like. What stands out to you here? High density, there's not really uniformity. It kind of looks like a mess. To be honest, like these are not like nicely packed shelves like you might see in grocery stores or in your home, or they're shelves, but they're really like holders for how people want to store items. Here we'll see an example of a human performing stowing as an action. So they scanned an item, they go over, move the translucent bands or elastic bands that are covering these fabric pods. They make room, right? You can see them like sort of trying to create space. Okay, they got the item in, maybe shoved the item in. Okay, back down, climb the ladder again, and back to the station. So what's our motivation for trying to tackle this problem? At Amazon, we really are looking at how to reduce the number of recurring roles where you're exercising a lot of physical effort. So for example, like going up and down the ladder, to reach the bottom bins, you might have to crouch down. So there's an aspect of like, hey, can we make this easier on our associates? And this looks like a cool problem that we should be solving because there are 60,000 of these in every building and we store a lot of inventory at any given point and pick a lot of inventory. From a manipulation aspect, this is an interesting problem because you have these fabric bands that are translucent. You want to estimate what the space is. You want to be able to maneuver in a small space which has multiple items. You don't have great modeling of like item to item interaction because the item set is something like 1 million different items. So can we actually do this? Can we automate or build a robot that can do this action? Then comes Stow. So this is our robotic arm. I'll let you all watch the video for a minute and then maybe go through and explain. So here, what humans are doing, contrary to what our previous human was doing, where they were trying to like make items go into places, here you're singulating items onto a conveyor. The conveyor is going down into this buffer wall where items are stored. Items are retrieved based on where we decide where we want to store. Just before we hand off to the store robot, we reorient, make sure we have good grasp of the item. We open the bands and we store the item. this looks fantastic, I think, in terms of a video. But now we will get into like, what did we have to do to like make this happen? And what were some of the trade-offs and challenges that we dealt with? So at a very high level, really focusing on that last bit that you saw, the action of stowing, what did we have to do there? You had to perceive and decide, right? Like what item do you want to store where? How do you want to store it? You want to open the bands. You want to make sure there is an item that you grasped. You want to make space in the bin, store the item, close the bands, verify that the item actually made it in, because there isn't a human that's supervising all of this. What are the key metrics that we care about? Rate is really important because humans are really good at it. Like if I ask you to like, create a shelf and, stock up a bunch of books, you would do that in relatively quick pace. So you want your robot to actually be able to keep up with that. You want to handle a wide range of items, right? Like as I mentioned, like any Amazon warehouse on average will have about 100 million items. And most of those are unique. And so that's quite a challenge to be able to model and handle that vast scale. You want to optimize for fullness of these bins, right? Like ultimately you're trying to store as much as possible into any of these bins. And so that's an aspect. You want to minimize damage and dropped items. This is part of like, making a reliable system, ensuring that it operates without you having to like go and, interrupt or clear things out from the stack. So let's dive into that first piece, which is the perceive and decide piece of it. So a bit of a closer look. I mentioned the bands that are over these pods. So you can kind of see those white lines in front of the fabric pod. This actually is quite challenging. So when you are, before anything else, you need to know, hey, where's the free space that I can actually use, right? So you want to know how occupied the bins are, how occupied each of the pods are, optimize for any n number of items that you have in hand to a pod face. To do this, you want to know where the bands are because you have to open them. You want to know where the bins are because you want to localize to that space. You want to know the occupancy of it, where there's free space. And potentially you want to know like where the walls are, where the bin lip is. And the bin lip is like that, where you see that 4G and 3G kind of naming. And that's relevant because we are actually using force in the loop. So we want to actually make contact at certain points and then move. The decide layer is interesting. This I often, like I think most people think of as it's a version of a knapsack problem where you're trying to get n items into m potential slots, like how would you do this? The interesting bit though is you're trying to also model your robot into it and the risk that's associated with any execution of a behavior. And you have a bunch of KPIs that you're trying to optimize over. So it's not only rate, it's not only damage, it's not only fullness. So there's like a cost function that's an Uber cost function that you're trying to optimize through. So with that as a context, I want to talk through some of the decisions that our team made early on and like how they panned out and how we probably had to revert and divert in the context of like maintaining modularity, thinking about the folks who are going to operate these robots and like what does that mean for like the overall Amazon ecosystem. Okay, so few years ago now, we started with this version of the pipeline. So I'm really going to focus on the perceive and decide. We had sensors that existed, we were figuring out feasibility. So you can imagine a large lab space, grab anything that's available to you, put it on the robot, let's play around and see what happens, right? So we had RGB cameras, we had a LiDAR that was used for like roughly localizing the pod, and then you're looking at, hey, like all of these things need to be detected that I talked about in the last slide, bands, bins, items. So let's use whatever model exists in order to put that pipeline together. And then you really start getting into, hey, what kind of behavior do you want to actually achieve, right? Like, for example, in the video that I showed, you have free space that's already created. You just need to throw the item in, right? You're just plunging it in. There, I think it's a more simpler problem. You're not trying to make space. And so it's pretty straightforward. You would handcraft an affordance, you execute that affordance. And the decision layer is focused around what should be the item to bin pair combination. So this will focus around geometric evaluation more than we focus around, hey, is this encoding the risk concept at all, right? So this was our first version. And I would say we did pretty well, right? Like for a feasibility concept, we got this implemented. We tried this a few thousand times, fairly reliable, high success rate, probably 90 plus. The challenges that we uncovered were interesting. We found the band separation problem quite hard, right? So because, as I mentioned, we were just using a LiDAR that had like one surface, we realized that the pod face is actually not flat. It's not a perpendicular surface. There are grooves. There's a variability within even warehouses as to where those bands are placed. So they might protrude 1 centimeter out onto the field. It might be 2 centimeters into the pod face. So localizing that band was actually a little bit more challenging than we expected. The occupancy models were working off of only 2D images in the beginning. And that, again, posed some challenges because when you have perspective, you have shadows, you have bin floors and walls at play, and that was also a challenge that we identified. This was mostly working well for cuboidal objects where everything still seemed very structured. At the same time, when we were uncovering these challenges, there was also like hardware revisions happening to the setup, right? So now is when it gets interesting. Does your original interface and API actually hold true, like as you uncover new problems and new challenges and you're iterating with your hardware? So here comes the next task where you're actually trying to create space, right? So take the video as like, this is your end goal. What would you potentially want to have in your API or in your modules that would enable this? As I mentioned, we identified a bunch of moving parts in like band separation that we had to overcome. And so we landed on, we took a hard look and decided, okay, like we're probably going to introduce n number of such behaviors where we're trying to rearrange the bin itself to make space. And to do that, we really need to like decouple the perception or like the pure CV portions out from affordance and decision layers. And so this is maybe the updated version of what those APIs look like, where your sensing is relatively still the same from your first version. Your semantic understanding piece has the models, you have the understanding in 2D and potentially in 3D space. And your affordance generation is still handcrafted. You still have interpretable geometric representations, and your decision layer is talking through the same strategy evaluation. So now I've highlighted some other additive and removal things that we did. As we were getting up on this task too, we wanted to introduce that new modality in 3D, right? We'd want to get rid of the LiDAR. So we went down the path of like introducing monocular depth prediction into the stack. Now, if I go back a couple of slides, let's see if I can move this. Previously, like anything to do with ML models lived in the scene understanding space, but to be honest, we're replacing a module in sensing, right? Like you're now getting depth instead of reading it as an active sensor. So I almost think immediately we broke that, we broke those modules, but continue to run through them. We introduced another task, which was more tight fit items. So you will see here, we seek the wall, we create space, and we eject item. By this time, we had actually moved to learn stereo. So you were using the same camera pairs that we were using for the rest of the stack, and you're also consolidating a lot of your models. So at this point, we were combining some of the semantic models into instant segmentation models, but not yet in a panoptic sense, because you always want to identify bands separately. So it was quite the journey. And these are only 3 tasks that I've outlined here, but there are actually a couple more that we implemented, and it's in our paper, but we probably have like 3 more that we're yet to come. So what did we learn from this? Some of the things that were tailwinds for us, like it was great to have like off-the-shelf models that we could play around with, put it on the stack, bootstrap, check out the feasibility of this task. Like, does it make sense? Will it survive in a Wild West setting? On the harder, what made it harder over the course of time though was your software architecture as you maintain these modules becomes more cumbersome. So for example, if you're trying to do any speed up of your entire coordination of the arm, you're now going to be throttled by how well you can do the message passing between all of these modules. And the overhead of communication with several different streams of inputs. So what should we do? I think I love this XKCD comic strip. I'll let you all read for a second. We could have gone and we could have said, yes, we're going to make this highly modular. We have these n number of tasks that we've identified, I don't know, 3 years ago, 5 years ago, 10 years ago. And we're going to make everything as modular as possible to achieve it. But then we probably wouldn't have a robot right now. Today, Stow has achieved something over 500,000 stores in 2 warehouses in the US and Germany. But that happened while we were revising hardware, revising our KPIs, understanding the space. So there is an element of modularity that, as much as it was constraining for the program and for us, I think it helped us make progress faster and get it out to the customer, but at the same time, learn more about the task itself. With that, how are we doing on time? Okay, yeah. So maybe we'll go quickly through these slides. So some things that we did that did help us in being faster about developing each of the modules and things that we're thinking about in the upcoming future that I want to touch on. We did leverage synthetic data for some of the more vision space things, right? Like we used Omniverse to render these pods. We had like diversity in these bands. We had diversity in the item set that we were looking at. We had a paper out actually in ICRA and with the data set released as well this year. But what we're hoping to really double down on is this sort of real to sim concept where we have a digital twin where we can play out some of the affordances. So if you see in the latest version of the modules that I talked about, affordance and the decision making are decoupled, and bringing those together to holistically evaluate affordances is where we're going to be investing. And that's also where I think like having real to sim and sim to real gaps be closed can help us move faster and potentially evaluate benchmarks better. And for this community, a quick call to action. I think you all probably see this also. I feel picking is reasonably well explored. There are several benchmarks, data sets that exist when you're looking at picking tasks. Whereas I still think like things where you're moving against gravity is not well explored. Rearrangement tasks haven't been explored as well. If we can think of interpretable VLAs, I think is my wish list. One of the biggest challenges is like when an operator says, "Hey, this robot is doing something funky." Think of a non-expert trying to really reason about why is your robot doing what it's doing. There's definitely benefit in exploring that space. And the last one, and we were talking during coffee chat as well, like the simulation space for like high density manipulation benchmark tasks, right? As you saw, those images don't look anything like a bookshelf or the organization in that. The diversity of items is quite high. So I think these are my sort of 3 areas that I would love to see more researchers invest in. With that, that's a wrap. We have a paper out on arXiv that's preprint. So if you want to read more details, like there's very detailed paper to see, and feel free to connect with me, and we can chat after this as well.